Connector, RIKEN, CCS. RIKEN itself is a big national lab. It's like Max Planck. So we are one of the 15 centers. We have other centers like AI centers, materials, biology, brain, and all that, regenerative medicine. But we are the HPC center, and in fact, we are the national flagship HPC center, research center. But I won't talk too much about research at our center today. There are lots of interesting stuff going on. But in the interest of time, we'll talk about our next machine, the Fugaku. So right now we had the K computer until which was decommissioned just a couple of months ago, August 16th, and of course many of you may know that the K was a very useful machine. Of course, it won lots of accolades in various rankings, also things like Gordon Bell Prizes. And in fact, one of the rankings, Graph 500, it retired as a #1 machine. So I think it's one of the first large-scale supercomputer to retain the #1 status and retire as such, because given the deflation of the value of the machine, after 8 years, usually you end up fairly low. But this, I think, it kind of shows the value of the design of the machine and how it's been able to sustain the performance. But all good things come to an end, and we had a big ceremony August 30th, and was attended by many politicians and was covered by TV stations. I gave a speech which was televised nationwide, and it was a very interesting moment. How people have such passion for a box full of silicon, the public interest. But it's really good, that we get the national backing. Well, of course, the machine have been retired to make room for our next machine, Fugaku. Fugaku is an alternative name for Mount Fuji, or we usually call it Fujisan, but Fugaku is a different alternative name. And we have started the construction and we'll start the installation process in a couple of months. And we expect that the operation will start in 2021, very early 21. Why do we name it Fugaku? Well, we went to a naming contest. We got like 5,000 entries from all around the world, which was great. But Fugaku kind of stood out, and also coincidentally, it signified my personal idealism about how a supercomputer should be. So on one hand, Mount Fuji, if people maybe probably seen a lot of pictures, maybe some of you may have climbed it. It's a standalone mountain, and as such has a very high peak. It's the highest peak in Japan, but also is very broad. So high peak signifies capability of the machine. That is, it stands out. There are lots of applications that require these types of very large capabilities to do unprecedented, for example, high resolution simulations. But to just build one machine for that purpose is not, it's not economically sustainable. You really want a very broad adoption, broad user base, broad sets of applications, not just simulation applications, but more other modern applications like data science, AI, and you want a very broad user base, not just with top-end academia, but the industry. In fact, you want the proliferation into the clouds, and by which you expand the market to other IT segments. So we believe it expresses this idealism. And so what's Fugaku? Well, this is just one slide description. So if you're sleepy like me and fall asleep, then just remember this slide for the specs. So we built a new ARM processor, which is extremely HPC optimized. So usually when you build a processor, as much as vendors like to claim, most processors are not designed for HPC, not optimized for HPC. They're optimized for like web workloads. But this is a bona fide HPC optimized processor, so it has very high bandwidth, has a terabyte per second theoretical peak, has embedded network, not across the I/O bus, but embedded into the memory subsystem. So with the injection bandwidth of nearly 400 gigabits per second per chip, and and along with ARM and also some of the other partners. The new instruction set SVE, the vector extension, was defined, and it's probably the world's first processor to support the SVE instruction extensions. And for this version, we get almost 3 teraflops, which is kind of going into the GPU territory. And also, it supports other more modern application data types, like, for example, that those appear in AI and deep learning, such as FP16, int8, short precision arithmetic, which can also be vectorized. So if you have int8, it's 64-way vector. But it's still a general purpose CPU. So when we first got this chip back in 2018, it booted a Red Hat Linux Enterprise without modification, right out of the box, which made us really happy, because the chip was functional, the A0 chip was functioning, and also it had no compatibility problems. So it was very good. It can also run Windows if you like, and it can run Word. It could be the fastest word processor in the world. And also, it's very power efficient, because most modern HPC machines are massively parallel, and power efficiency basically limits the scale of the machine. So it's tantamount that the processor is very power efficient. And in some of the workloads, we see up to order of magnitude better power efficiency compared to conventional CPUs. So we take that CPU that we designed with Fujitsu, and we assemble 150,000 of them into a single machine. So this supersedes the Livermore's Sequoia as the supercomputer ever to have the largest number of nodes. So in aggregate, we have 150 petabytes per second of memory bandwidth in the system, which basically is about 7 times that of a Oak Ridge Summit. And the ejection bandwidth to the network as such is about 50 to 60 petabits per second, which is about 10 times the global IDC traffic if you aggregate all the Amazons and Googles and all their hyperscale data centers. Their internal traffic is about 5 petabits per second. So it's about 10. So the network has about 10 times the capacity in injection, and it has other features. So in some ways, it's the first exascale machine. It's the machine to realize not necessarily the 64-bit exaflops, but it's the first machine to realize what we envision as the exascale performance expectations that people had when we started talking about exascale back in let's say in the late 2000s and early 2010s. So, and that's coming to you next year. And we have been working on this for the past, actually we have been working on this for the past 10 years, even before K was launched. So the first incarnation of the discussion material about this machine, actually we started doing this in 2010. And I was of course I was a major part of this. And then 2012 K was built and launched, but the study went on. And 2014, officially there was sort of a precursor project, feasibility study, by which we basically defined the architecture parameters. And then in 2014, officially the development project was launched. And now we're in 2019, and as you have seen, we have decommissioned K, and we're just about to have the first racks being shipped to it. But of course, it's been long years of work. So how do we HPC optimize? Well, so it was through the co-design process, because it was identified even early on globally amongst all the exascale projects that co-design was going to be very important, in fact, tantamount to the system design, because of the fact that it would be very difficult to build exascale machines because the parameters are so challenging. So what we have done is to basically recruit all the application people in Japan, and many of those use K and other supercomputers. Then we had RIKEN. We established a center. So my center was established 8 years ago, and had a different director, but it was established 8 years ago. And then along with Fujitsu, we basically conducted rounds of this co-design process, the so-called co-design process, figuring out what were the essential parameters, what are the bottlenecks, what are the right parameters for the applications. Not to like shoot for exascale limp pack, number, which is complete foolish because that has very little correlation with real application performance. Rather, we try to, the goal was set to achieve up to 100 times speed up, typically about 30 to 40 to 50, but up to 100 times speed up on the applications running on the K computer. And of course, ease of programming and robust code base and all those were also set, and very extreme power efficiency was set as the design goal. And what were the applications? Well, there were several rounds of application programs, but for Fugaku in 2014, as the Fugaku was launched, this what are called the 9 priority issues, so priority areas were established, and these were led by the top application teams in the country. But if you look at these in detail, these are mostly application areas of great concern to the public, to the taxpayers. So one is medical, the green part. So this is medical, like pharmaceuticals. Okay. No beam. Laser pointer. Trust me. Okay. All right. So, oops. Yeah. Ooh, that was bad. Yeah. So we had like medical, pharmaceutical. We had disaster prevention, environment. Of course, we're hit with typhoons all the time. Hopefully the match between Scotland and Japan will not be canceled. But I'd like to see the match. But I build out here before the match ends because I don't want to get mugged by that. In case we win. There's energy is important. Energy generation, storage, transmission is very important. And then in the industry, as we have seen in previous talk, things like turbines, automotives, and also materials, various types of materials. These are very important. And then there's a little bit of basic science here as well, which actually inspires the public. So again, these are the application areas were chosen to basically advance the not just pure science, but the industry as a whole. And I can go over all the applications, but very brief. A very large scale molecular dynamics, multi-proteomics for drug design, environment. Sub-kilometer mesh climate simulation, which was done on K, but will be accelerated by a factor of 100 on Fugaku. Organ simulations like heart, with very precise emulation of not just the muscle cells, but also all the signals, electrical pulses, the circulatory systems, the blood circulations and everything. And then, of course, big data observation, assimilation with the simulation is very important. So real-time assimilation of data with the simulation. For example, in climate, where we will expect to have terabyte per second class data in stream coming to, and then doing some statistical matching of the observation to the observed parameters and all that. So and I can go on. There are many application areas that are being prepped to run on Fugaku. So we have achieved this. So I think we'll be achieving. One of the goals was to have a continuum from K, in fact, 100 times faster up to applications. But but in a review of the architecture, there were also some issues with K, and for that reason, K was in some ways a commercial disaster. Right? Didn't really. You don't see any remnants, for example, the K in UK, and why you see lots of Intel and other processors here. So why is that? Well, there are several factors. One was, when we review the processor performance, K as a machine was very good. Its scale had about 84,000 nodes. So as a parallel machine, it was good. But each of the processor was on par, let's say, compared to the latest Intels of the day. We know because we did a lot of comparative performance studies. And when you have a processor, which is Intel, x86, robust ecosystem, you have a Spark FX8, which is Spark, and only with a single chip, then has we still remember the glorious Sundays, but I'm sorry, the ecosystem going down. So there's no compelling reason to buy this. But this time, so what we really had shot for is to achieve significant performance advantage over existing processors. 3 times, 4 times, factors performance advantage. And also it had to be very green. K was not necessarily a very green machine. So it was okay, but was not very green. So again, we had to shoot for extreme greenness, and that was set as one of the priority design goals. And then the ecosystem question, the software. So the ecosystem, computers are all about ecosystems. So how do we establish a very robust ecosystem? Well, from my perspective, there are only 2 choices. There's x86 and ARM. But it's very hard to get an x86 license. And ARM was the obvious choice because ARM sells 20 billion CPUs per year. But of course, mostly in the edge space. But then they're coming up to the servers as well. So what we plan on doing is to build a pinnacle ARM processor. That would be like the top of the entire ARM ecosystem. And then build in new features that will be amenable to application areas, not just within simulation, but outside in what we call in Japan called the Society 5.0 applications. Those with AI, big data, blockchain, and all those new breeds of applications. So with those design goals in mind, the processor was designed, and of course the system was designed, and that's the processor you see. And it's being fabbed on TSMC 7 nanometers. And so in some sense, it's a hallmark of UK, because ARM is a UK engineering outcome. And of course, Fujitsu is a Japanese company. Well, ARM is a Japanese company now, but still has a headquarters in Cambridge, so it's still UK engineering. So it's sort of a hallmark of joint UK and Japan engineering, the pinnacle of to have built up this pinnacle CPU. It has 52 cores. So there are lots of details I can speak about the processor, but just to give you a very nutshell sort of a characterization is, on one hand, it is like a mini-core ARM CPU, and in fact it is. But we have not taken any of the ARM core microarchitectural design. The microarchitecture was entirely done by Fujitsu and us. Well, of course, most by Fujitsu. So, but it still, of course, runs all the ARM code. It's compliant to all the ARM standards, instruction set, also all the server specifications and so forth. So, that's why I booted the Red Hat out of the box. But characteristically, it has lots of elements as a streaming processor because it has very wide vector and has very high memory bandwidth. So the only way to get performance is to architect the chip as not just a CPU, but have a very wide data path and memory enhancements to allow the data to stream through and compute it with the vector units. So, which is exactly what the classical vector machines were, and now sort of inherited to or by GPUs. So, so it's sort of it's not to say it has a GPU embedded, it's still a CPU, but architecturally, if you look at each core, it has lots of elements that you may also see in the GPU. So, so for example, there are what are called 4 CMGs, core memory groups, and each core memory group has 13 cores, of which 12 are given to the user. But each of the core, but within a CMG, each core, every core is linked with others using crossbar, using a crossbar fabric instead of, let's say, using a mesh or like ring topology. Ring topology connects to CMGs, but within a CMG, you get very high bandwidth between the cores, and also very high bandwidth to the shared L2, and then to the HBM memory controller. And also, the cache transactions are asynchronous. So, it just lets the data stream through, just like a GPU. So the performance of the aggregate performance at the L1 level is about 11 terabytes per second, which is bytes per flop being 4. So you can do simultaneous loads and stores into the cache unit, with 5 and 12-bit SIMD. And also it has enhancement features. For example, it can sustain unaligned loads and 120 byte per cycle load. That can do unaligned loads to L1 cache, which typically is a problem. And it also has memory aggregation features. This is like also like a GPU. It can do combined gather, so it can do gather scatter, but in a strided fashion. But it can access actually 2 words from 128 byte blocks. So it's sort of an aggregation feature. And then it has a power saving feature. Like I said, the processor is already very power efficient, and by design, it's a GPU level power efficiency instead of CPU. We get some. We have already announced we get something like on a Green 500, which is not the best representation of this chip. We get somewhere 15 gigabytes per 16 gigaflops per watt, which is like 3 times better than any other CPU and pretty much equivalent to Volta. But also has more other features. You can actually turn on and off the execution units depending on your workload. So if you have like memory-bound workloads, having the compute pipe turned on doesn't make sense. So then you can turn them off to get maximum power efficiency. Aside from the frequency, voltage, the normal frequency and voltage adjustments. So what's the real performance? Well, we've been banging on Fujitsu, trying to have them release performance numbers, but they're very cautious. But I'll give you a few numbers. I expect that for SC and maybe subsequently towards winter and spring, we'll be able to announce more numbers. Right now, this is a Himeno benchmark. This is a Fortran 90, very simple Poisson solver, very popular Poisson solver benchmark. Here we get Xeon Platinum. This is a Skylake, but pretty much the same with Cascade Lake. Well, 2 chips on a single node with 2 chips, you get about 85 gigaflops, and on Fugaku you get about 346. So per node is 4 times, but remember it's a 2-chip node on Intel. So on a per chip basis, it's about 8 times faster. And that's really proportional to the amount of memory bandwidth per chip available. But it's even more, but it's even more efficient, faster than XX Aurora, NEC's XX Aurora, or the Tesla V100. And actually, Aurora, NEC just announced that they will come up with a new version of Aurora, which will be coming out in like late 21. But still, even with that, they're on par with this chip. So you can see that can even compare to vector processors, both classical vector and GPUs. This chip also has the vector throughput characteristics to sustain the performance. For real codes, of course, like weather forecasts, like WRF, the difference, of course, shrinks because there are some integer components. There are divergencies in code with various boundary conditions and so forth. So, so the difference, of course, shrinks because Intel is very good at doing those. But even so, the difference is about, on a per chip basis, on this particular WRF benchmark, is about a factor of 3. So about 50% faster per node, or about a factor of 3 if you do a chip-to-chip comparison. So this is the configuration for Fugaku. It's water-cooled, but there'll be other form factors provided by various vendors, hopefully. And in this configuration, it's water-cooled, and it'll have 384 nodes per rack, and we'll have hundreds of racks. Interconnect Tofu is about 40 gigabytes per second, and it's connected directly to the memory bus, the memory ring bus, with multiple DMACs that you can shoot data to all 6 directions. So of course the throughput, you get about 38 gigabytes per second. But because of this memory being linked to the memory bus, you can do things like cache injection to the L2 cache to the other nodes. So this greatly reduces latency. We've seen something like 30% reduction in latency. So the ping pong latency between the 2 nodes is about half a microsecond, which is faster than any other network in the world, I think. And this, of course, scaled to 150,000 nodes. so this, but again, there will be different form factors, but this is a scalable form factor that we built for us by Fujitsu. Given 150,000 nodes, we have nearly 8 million cores, and the power maximum is about, for the data center, we have about 40 megawatts, but a normal production we expect to see somewhere around 30, including cooling and so forth. So, but NRE we think really paid off, because had we built this out of conventional off-the-shelf processors, the machine would have been maybe 3 times as big, and cost 3 times as big, and use 3 times more power. So the NRE, we believe, although it did did have some costs incurred for development, even with the machine alone, it already has some impact in terms of cost reduction by several factors, let alone its potential commercial implications. Now that Fujitsu can go to other markets and sell the chip, and we are achieving. This is real measurements on the chip and the projected performance, and we will achieve about an average of 40 on these key applications, benchmark apps, and then some apps will go over 100 times, because, for example, we can use reduce precision arithmetic and other new features on the machine. And the software will be all standard. Just it'll look like it's a big ARM cluster, so just like a big x86 cluster, nothing else. So it'll have everything. It will be just standard. Not just HPC software stack, but it'll have, it can run Python, it can run Julia, it can run everything. It can run containers. We plan on supporting Singularity as the default container in production. Of course, can run KVM and other things. We are working. I'll give 30-second spiel later, but we're working with various parties to enhance the AI software stack, and we'll be using SPAC. Collaboration with Livermore to enhance the SPAC package manager for managing all the HPC software. In fact, we're already testing, and it runs multiple compilers, GCC, LLVM, ARM, Fujitsu. There are a few patches here and there that's needed, but usually it's like very minor. Define AARC64 or something like that. So most of the codes and this has been reported by others, that most of the codes do run on this chip, even the SVE. So given that, we have plans on expanding this to the cloud. So hopefully, we're working with cloud vendors to provide this to the cloud initially as a resource, but eventually, of course, the hope is this chip will go into the hyperscalers in millions. Well, Fujitsu. So there was a curious announcement. I'm sorry, I'll end in a few minutes. There was a curious announcement, which was on the NSF webpage, that said, Stony Brook is acquiring a new machine. And it says it's getting an A64FX-based Cray machine called Okami, which is a wolf in Japanese. I have no further comment about this, but that's what NSF says, okay, and the Stony Brook says. So it's apparently the installation will happen next year. Okay, so Cray A64FX machine. Okay, so I'll skip most of the AI stuff. Just one word that we are working with ARM research with people in Cambridge, Fujitsu Labs, people in Tokyo, and of course our center and several other collaborators to try to have optimized performance on deep learning software stacks, because the capability of the chip itself may not be quite as good as the top-end GPUs, but can come fairly close, given the flops count and so forth. So because there are like support for convolutional operators in the instruction sets. So if you do like ISO power analysis of, let's say, Volta versus A64FX, so it's about two A64FX chips versus 1 Volta will be about ISO power. You can see that the numbers are pretty much similar. in terms of compute performance, except for the tensor cores. So, so we believe that if we do the right implementation, we can do very good deep learning training on this chip. Okay. Okay. So that's with that. Hopefully we can report to you some more performance numbers in the upcoming HPC forum, and also the real photo of the real installation of the machine, which coming to you this winter. Okay, thank you very much.
Excellent.